Alright, so yesterday you guys did a lab where you looked at how force, acceleration, velocity, motion, they were all kind of related. And you guys came up with a pretty good conclusion. You came up with the fact that forces cause acceleration. Okay? And that is absolutely true. In fact, that's just a fancy way of stating Newton's first law. Okay? Newton's first law says an object's motion will not change unless a force acts on it. Okay? We're going to actually change this just a little bit. Okay? You guys might have heard Newton's first law stated as an object in motion stays in motion, an object at rest stays at rest unless it's acted upon by an outside force. Okay, same thing, this is just a more concise way to put it. But I'm going to go just a little bit more with this force. Okay, because I had you guys draw the free body diagram for the cart sitting on the track yesterday. So here's my cart, we had a string pulling on it, and I said, okay, label all the forces. So there's this force, which is the tension in the string. But there's also this force and this force. Okay? This is the force due to gravity, and this is the force of the surface pushing up. That's called the normal force. It's the force that always acts from a surface perpendicular to the surface. Okay? So there's actually three forces on this cart. Okay? But these two, they don't matter because they cancel each other out. Forces are vectors, so when you add them together, forces in the same direction get bigger, forces in opposite direction subtract, right? So those are zero. So what I can say is I can say the total force, or the sum of the forces, okay, the sigma means sum of, okay, this is net force, okay, the total force acting in the y direction, okay, so I'm going to say net force in the vertical direction is zero. That's not the same thing as saying there's no forces acting in the vertical direction. It's just that they cancel each other out. Okay? And so we didn't have to worry about these two. All we had to worry about was the tension in the string. Okay? Now Newton's first law is also called the principle of inertia. And I had you guys take the mass off of the cart and redo the experiment. And you notice when you did that, the cart accelerated faster. Okay? That's because there was less mass. Okay? Well, mass is the measure of inertia. Okay? And if you recall from your freshman year, okay, inertia is resistance to change. Okay? So the more mass something has, the harder it is to change its motion. The less mass something has, the easier it is to change its motion, which is really what Newton's second law says. Okay? And so this was also sort of the second part of that. Newton's second law is an equation. Okay? Newton's second law just simply says that the total force acting on an object is equal to the mass times the acceleration. Okay? So total force, net force, equals mass times acceleration. Okay? It's really as straightforward as that. Okay? So there's a practice problem on page 95 that says, hey, a canoe is sitting here and somebody starts to pull on it, and somebody pulls with a force of 165 newtons and somebody else pulls in the same direction with a force of 225 newtons, and they want to know what's the net force acting on that canoe. Well, duh, we add those up, right? We're going to take 165 plus 225, which equals 390 newtons, right? Force is measured in newtons. Okay. The second problem says, well, what if instead of them pulling together, they pulled opposite? So we had our 165 newtons this way. Okay, well, now it's pretty important that I establish a positive direction, so I'm going to call this positive. Okay, and so now I have the net force is equal to 225 plus a negative 165. It's a negative 165 because it pulls backwards. Okay? And this equals 60 newtons. Okay? And so you can see net force is the sum of the forces acting on the object. Okay? Now, what if I didn't want any force acting on it at all? Well, since there's 60 newtons acting to the right, I would need an extra 60 newtons acting to the left. Okay, so if somebody pulled this way with a force of 60 newtons, okay, I don't know if the canoe is moving or not. I do know now that the canoe is not accelerating because now the total force is equal to 0. And this force right here that we just added, okay, this put the whole system in equilibrium. Okay, so a system in equilibrium, the net force is 0. So all the forces, once we add them together, they add up to 0. And that just means no acceleration. Doesn't mean no motion, means no acceleration. Okay, so an equilibriant is the force that cancels out all the rest of them. Okay, that's 60 newtons combined with that 165 cancels out the 225, so our forces are in equilibrium. Now I could take this problem one step further and say, okay, so what if we just consider the first case of the canoe, when it had two forces acting on it, the 165 this way and the 225 this way. Was it 165 and 225? I think it was. Okay. How much force? And let's say that the canoe has a mass of 20 kilograms. Okay. I want to know the acceleration of the canoe. Well, then I can use Newton's second law, which is net force equals mass times acceleration. So I take 165 plus 225 equals 20 times a. So 390 equals 20a. Divide by 20, divide by 20, and a equals 19.5 meters per second. Right? That's the acceleration. So this canoe would actually start to go pretty fast. Okay, so I doubt that's a realistic situation, but there it is. Okay, okay, that's Newton's second law, and yeah, it'll get more complicated when we start adding more forces, but we're going to keep it pretty simple for now. Okay, so what I want you guys to do is I want you to try to work a few problems for me. On page 95, there are problems 9 through 14, and I want you to attempt those. Some of them are pictures, some of them are identifying things. Now, there's also a table on page 94 that goes through some common forces that we're going to deal with, forces like friction, the normal force, the force in a spring, the tension force, thrust, weight. Okay, it's going to be all of those things, and I want you to read through that table and get a little bit familiar with those forces because we're going to use them over and over and over again. Okay, so look at the table, answer the questions on page 95. You can either do it in your notebook. I kind of want to see your answers 9 through 14, so either do it in a notebook and take a picture of it so you can email it to me, or do it in Notability and email it to me. Okay, good luck with that. Let me know if you have any questions. You can come see me in homeroom or shoot me an email.